Hello there, and welcome to this live edition of the Chemistry Clinic brought to you by Boost Revision. If you're joining us for this session, we're live on YouTube, and today's session is going to be a mid-year review on organic chemistry for year 13. Now, if you are on YouTube or watching this live, please do use the chat box to leave questions for us. I will switch over intermittently to YouTube to check for any questions that you've got for us. Okay, so before we start, I'm going to connect my iPad to this session, and then we'll start by looking at some of the key syllabus points in your specification. So if you bear with me 1 second, I will switch over shortly. Okay. Okay, so you should be able to see the specification, and I have moved on to the part to do with Module 6, which is the organic chemistry section in the second year of the course. Now, there are a number of topics that we need to take into consideration here. The first, of course, is aromatic chemistry, so the chemistry of benzene and all its reactions. We'll also be looking at carboxylic acids and esters, organic nitrogen compounds, so these are amines and amino acids, and of course amides as well, which you will have encountered. We'll also look at polymerization, and we'll focus on condensation polymers, and perhaps if we do have time, we'll look at a little bit of addition polymerization as well, and of course how we can bring all of these different topics together to carry out synthesis of reaction targets. And it is important to note that even though we're going to be focusing on these questions, there are topics from the first year, so those highlighted in yellow on the same page, which will be covered in an indirect way when we look at the organic chemistry topics that I've just mentioned. And I think it's also important to make this point that when revising organic chemistry, it's good to test yourself to see how much you know in the way of the different reactions that each functional group undergoes, so all the different conversions you can make. Test yourself on the reaction conditions, and then ask yourself what mechanisms are involved and whether you can draw them. So we will look at how you can start a reaction scheme containing lots of different reactions, and then we'll look at different mechanisms that may or may not be involved. Okay, so without further ado, we're going to start on aromatic chemistry. Okay, so you're all familiar with benzene, and we can see the delocalized pi electron system, which I've highlighted in yellow here. And I wouldn't spend too much time describing the bonding and structure of benzene, but I will certainly ask you to review that so that you understand fully why benzene reacts in the way it does. But because we're limited in the amount of time we've got here, I'm going to sort of quickly look at the different reactions that you need to know as far as benzene is concerned. Okay, so we know that benzene is electron poor. It's not as nucleophilic as an alkene, and so it will undergo substitution reactions. Okay, so one substitution reaction that benzene can undergo is, of course, a nitration of benzene. Okay, so you can have an NO2 group as such. Okay, so we'll look very shortly at how that is achieved. Another reaction, a substitution reaction involving benzene, is when you halogenate it. So we can have benzene and perhaps a bromine group replacing one of the hydrogens on your benzene molecule. Another thing we can do with benzene is, of course, to acylate it. So if we think back to the Friedel-Crafts acylation, so okay, so that would lead to that benzene compound shown there. Okay, so 3 different reactions involving the electrophilic substitution mechanism. And of course, we can also go on to do or reduce the nitro group to the amine, so something that you should be familiar with. There's an NH2 group there. And of course, we can also compare the reaction of benzene with other aromatic molecules such as phenol. Okay, and also the phenylamine that we've just made. Okay, so looking at the first structure that we drew, which is nitrobenzene, if I highlight that in pink, or rather yellow here. So we've got nitrobenzene, and in order to form nitrobenzene, of course, you will need to have concentrated nitric acid, and you do need concentrated sulfuric acid. Okay, and why is that? Because you need to form this nitrating mixture where NO2 plus is the electrophile formed. Okay, so those are the conditions required. If you're wondering what this reaction looks like, so you would need HNO3 plus H2SO4, and that initially will form H2NO3 plus and HSO4 minus, and then your H2NO3 plus will break down to give you your a water molecule and your NO2 plus species. Okay, so it's the NO2 plus species that is the electrophile in this reaction. Okay, and we'll look at the mechanism very shortly. As far as reducing the nitro group to the amine, you will need a reducing agent. In this case, reducing agent is tin and hydrochloric acid, concentrated hydrochloric acid. It's about 6 molar hydrochloric acid, and that will reduce the nitro group to the amine. Okay, so far we've carried out some conversions, and they all proceed via the same mechanism. We'll look at the mechanism very shortly. If you're trying to brominate benzene, then you will need a halogen carrier catalyst, such as in this instance AlBr3, and you would need Br2 as well. So the AlBr3 reacts with Br2 to form AlBr4 minus and the Br plus electrophile. So just as we saw with the formation of the NO2 plus electrophile, we need a Br plus electrophile so that benzene can the pi electrons can actually attack that electrophile. So if we write an equation there, we're going to have AlBr3 plus Br2 going to AlBr4 minus and Br plus. Okay, and if we highlight the electrophile, it is this Br plus species. Okay, so that's another reaction out of the way, and it's in a similar manner your acylation. So this is your acyl group. If I highlight the acyl group in pink here, that acyl group has to be formed from the reaction of Al. So that's AlCl3 plus your acyl chloride. Okay, so that would form AlCl4 minus and your acydium ion. Okay, and again, that is your electrophile, so this acydium species here. Okay, so what you can see with benzene is that all of the electrophiles it reacts with have got a formal positive charge on them. So it's a full plus charge to give you the electrophilic species. Okay. Now, if you contrast that with phenol, phenol can react with bromine without the need for the formation of an electrophile with a plus charge on it. Okay, so we could simply look at the formation of bromophenol. Okay. And HBr. And there is no need for a halogen carrier catalyst. And remember that this is because the pi electron density in phenol is richer than you would find in benzene. The lone pair on the oxygen of the OH group will delocalize into the pi electron system of benzene, making it more electron rich, and that means that it is a better nucleophile and can attack our Br2 molecule. Okay, so contrast that with what happens when benzene reacts with any of the other electrophilic species. It's a lot less reactive than phenol. Like the other thing to note about phenol is that it is weakly acidic, so it will react with an alkali to give you to form a salt. Okay, so let's look at the mechanism of the electrophilic substitution of benzene then. Okay, so if we take benzene and react it with a generic electrophile, so if I show benzene again, and benzene is being reacted with an electrophile, I'm going to represent that electrophile with a capital E and a plus charge. So it could be NO2 plus, it could be Br plus, it could be the acylium species. Okay, so to draw the mechanism, you need a curly arrow from the pi electron density drawn to the electrophile. Okay, there should be no ambiguity at all. It should start from the inner ring, and as a result of this attack of the electrophile, you will be left with an intermediate which looks like this. Okay, so you've disrupted or broken the aromaticity of benzene. You've used up two of its pi electrons to form a bond to the electrophile. Okay, so the bond formed to the electrophile there is highlighted in yellow. And as a result, you've got a very unstable intermediate, which is no longer aromatic. And because it is unstable, there is a driving force towards restoring aromaticity and giving you back an aromatic compound. And the way that happens is that the electrons in the carbon-hydrogen bond I've shown in blue are used to restore the full complement of 6 pi electrons. And to show that, you need a curly arrow from the middle of that bond into the remaining pi electrons, so that you now have 6 pi electrons altogether, and the replacement of the hydrogen, hence a substitution reaction. Okay, so we've got our species shown there, and of course you will have an H plus ion as a byproduct. Okay, so all of the electrophilic substitution mechanisms proceed in the way shown here. Okay, so that's a sort of a whirlwind tour of some of the reactions of benzene and its derivatives. So as far as aromatic compounds are concerned, you want to remember the electrophilic substitution mechanisms. If we label this as that, so electrophilic substitution. Okay, good. So so that's benzene and aromatic chemistry. If there are any questions at all, I'm just very going to quickly check on YouTube to see if there are. There's nothing in the chat box at the minute. Okay, so we will continue with our work so moving on to carboxylic acids and esters, and in essence looking at carbonyl compounds. So let's do exactly that. Okay. So moving on to carbonyl compounds. Of course, the carbonyl group should be, but at this stage, familiar to all of you, and it comprises a C double bond O. So you can have, as an example, an aldehyde shown here. So in this case, ethanol, or you could have a ketone, as shown here, and you may, of course, have a carboxylic acid, shown like so. And if you then consider that we could have an ester, which is the result of the carboxylic acid reacting with an alcohol, so an ester in this case ethyl ethanoate shown there. You can also have a carbonyl group in an acyl chloride, so in this case ethanoyl chloride. These are all examples of the compounds containing the carbonyl group. So C double bond O is shown there. Okay, so we can sort of essentially draw a similar reaction scheme like we did for benzene, showing all the different transformations we can make to firstly form a compound containing a carbonyl group, and then also to look at all the different reactions that we can carry out on the carbonyl functional group. Okay, so let's start with this alcohol here. Okay, so you've got ethanol, and of course, if you oxidize your ethanol, you should be able to make the aldehyde ethanal, so drawn as so. Okay, and depending on how much oxidizing agent you use, if you use 2 equivalents of your acidified potassium dichromate, you could oxidize that all the way to the carboxylic acid. Okay, so there's ethanoic acid shown there, and so that's ethanol, and we can of course isolate the aldehyde which we've drawn already, ethanol, and then oxidize it in a separate reaction to the carboxylic acid. So perhaps if we just show the arrow going down that way. Okay, so that's 2 or rather 3 different reactions you can do starting from ethanol. Okay, now the way to access a ketone would be to well, let's before we talk about ketones, let's look at the reagents that you would need. So you would need acidified potassium dichromate or ammonium dichromate, Y13. Okay, and in the case of this reaction, we would need to distill the product so that we don't have sort of further oxidation of the aldehyde to the carboxylic acid. Okay, and if you want to oxidize further to the carboxylic acid, again, it'd be the same reagents, and you might consider refluxing it. And it would be the same if you were going all the way to the carboxylic acid straight from the alcohol. Okay, so K2Cr2O7, and you would need to reflux that. Okay, so that's how you would get to your carboxylic acid. If you wanted to make a ketone, you would need to start from a different alcohol. So ketones can be accessed from secondary alcohols. So if we had propan-2-ol, for instance, shown there, you could oxidize it. So acidified potassium dichromate again, and that would lead to your ketone. Now, in the oxidation of the alcohol, you will also form water as a byproduct. Now, I haven't shown water in my reaction scheme. When you do write a balanced equation, you should consider the fact that water is formed. So only 1 mole of water is formed when you oxidize your alcohol all the way to the carboxylic acid. Okay, so do write a balanced equation just to show that you do understand what's going on. Okay, so we've got different compounds shown on the screen. Let's look at how you can go from your carboxylic acid to an ester, for instance. Okay, so if you wanted to make an ester, so let's say ethyl ethanoate, you would need to react your carboxylic acid with some ethanol, so in this case ethanol, and you would need an acid catalyst to give you your ester. Okay, so as well as forming the ester, it's a condensation reaction, remember, so you will form a molecule of water. Now, we'll very shortly look at so we'll very shortly look at how you can go backwards because you do actually establish an equilibrium. And the fact is that your carboxylic acid is not very reactive when you're trying to make an ester, and so it's important that you use a carboxylic acid derivative such as your acyl chloride or even an acid anhydride to allow you to access the ester quite quickly. So alternatively, you could, if we do this in red to show formation of our ethyl ethanoate, you should, or you could use your acyl chloride, ethanoyl chloride, and you could then react that with your ethanol. Okay, and that is much faster, but will has the disadvantage of producing hydrogen chloride. And you could use an acid anhydride, such as ethanoic anhydride, and then that way you don't have the harmful, well, sorry, not harmful, but the very corrosive hydrogen chloride product being formed. You would have ethanoic acid as a byproduct in that particular reaction. Okay, so we've looked at sort of oxidations to form our aldehyde and ketone. We've also looked at oxidations to form carboxylic acid, and then using the carboxylic acid to form an ester. Okay, and of course you can also use an acyl chloride to form an ester by reacting it with an alcohol. Okay, so going through this exercise, trying to recall all the different transformations you can make is very important. Now, so far we've looked at oxidations, but we can also go backwards. And so you can, if you wish to, go from your aldehyde back to your alcohol, for instance. So if we show this in a different color, perhaps, let's go red. So we could potentially go backwards like so, and in doing that, you would need a reducing agent. So sodium borohydride might be the reducing agent of choice. There are, of course, others such as lithium aluminium hydride. So you could reduce your aldehyde. You could also reduce your carboxylic acid all the way back to the alcohol. So lithium aluminium hydride might be a reagent of choice. And then as far as the esters go, you can actually hydrolyze these esters back to carboxylic acid. So in this instance, they would involve the same sort of acidic or sometimes alkaline conditions to go back to your carboxylic acid. So hydrolysis, H plus hydrolysis to go back to your carboxylic acid. So quite a few reactions that you can think about and should sort of have at your fingertips as far as these carbonyl containing compounds are concerned. Okay, so let's have a look at sort of mechanisms. Now we've looked at, we've just described how you can reduce your carbonyl group, so your aldehyde or your ketone, back to the alcohol. And of course, this involves the nucleophilic addition mechanism. So if you've got an aldehyde as shown here, and you wanted to reduce it, you would need to react it with a reducing agent. And shorthand for our reducing agent is H in square brackets. And in doing that, you will be reducing it to the alcohol. Okay, so we need to consider how many equivalents of our reducing agent we would need to be reacting with our aldehyde. So the aldehyde has got 4 hydrogens, but your alcohol has got 6 hydrogens in total. So you will need 2 equivalents of your reducing agent, so sodium borohydride or lithium aluminium hydride. Now, as far as the mechanism goes, it's simplified to show the reducing agent as the hydride ion. The hydride ion is, of course, the H- ion. It's got a lone pair on it, and it is a nucleophile. Okay, so it's an electron pair donor. It's going to attack the carbonyl. Why is it able to attack the carbonyl group? Well, the carbonyl group has a delta plus there and a delta minus there, owing to the electronegativity of oxygen versus carbon. Okay, so if we draw a curly arrow from the lone pair of our hydride to the carbon with a delta plus on it, and then show the breaking of the pi bond in your carbonyl group, like so, and that should lead to the formation of this intermediate shown here, and there's the hydrogen that we've just attached. Okay, so we've got that intermediate formed, and of course, if you pay attention to the charges, we've got a minus charge here, just as we had a minus charge over on the other side of the arrow. So the charge is always conserved. Always make sure that you're checking the charges of intermediates. Now, the second equivalent of your hydrogen is needed to go to the alcohol, and this typically comes from a solvent molecule. So again, we've got a simplified mechanism here, and the lone pair on the oxygen attacks the H plus to give you the OH group. Okay, so this is a nucleophilic addition to a carbonyl group. Okay, so that's your mechanism. So with the carbonyls, as far as the OCR course is concerned, you aren't required to know much more than the nucleophilic addition mechanism. One thing that catches students out quite a bit is not paying attention to the stoichiometry of your equation and making sure that you've got the right number of moles of your reducing agent to reduce your carbonide. So if you pay attention here, you've got one equivalent of hydrogen there, and there's the second equivalent of hydrogen there, and that allows you to form your ethanol from your aldehyde. Okay, so reducing a ketone would proceed in much the same way. Okay, so that's so a very quick tour of carbonyls, and if we very quickly check on YouTube to see if there are any questions. Currently, no questions on YouTube, so we will carry on with our work. Okay, so we've now looked at aromatic chemistry. We've also looked at carbonyls, and if we go back to our spec, the next thing that we might want to sort of consider is amines and amino acids. So we can very quickly look at these organic nitrogen-containing compounds. So what does an amine look like? So amines are derivatives of ammonia. If you remember, ammonia has a formula NH3. Okay, so if we replace one of the hydrogens of our ammonia with an alkyl group, you will end up with a primary amine. So primary amine would look like that. So an example is methylamine, which is shown here. A secondary amine will have two alkyl groups, so that would be dimethylamine, and you could have a tertiary amine, of course. So trimethylamine would be the example. So if we primary, secondary, and tertiary amines, and of course you could have a quaternary ammonium salt. So you may well have something that looks a bit like this. Okay, so and has a plus charge on it. Okay, so this would be a quaternary ammonium salt. So okay, so with your salt, if we showed its counter ion, so it could be tetramethyl ammonium chloride, for instance. Okay, so quaternary ammonium species. Good. So these are all derivatives of ammonia, and of course you can have the two important things to note about these species, and the fact that ammonia is basic, and so you do have the amines being having basic properties as well. So they will behave as bases, and they will behave as nucleophiles as well. So a few things to note about these species: so basic, and they'll be nucleophilic. Nucleophilic because the nitrogen of your ammonia or your amines contain have a pair of electrons, a lone pair that they can donate. So they are an electron pair donor. If I quickly show these lone pairs, so there's one lone pair there, there's another. Okay, and the quaternary ammonium doesn't have a lone pair. It's used its lone pair to form a bond, so hence the plus charge. Okay, so they're basic or nucleophilic, and we can as we're looking at amines, we can also have a quick look at amino acids, and these are very important in forming polypeptides, which of course are then sort of folded into sort of a secondary or tertiary structure to give you proteins. Okay, so amino acids or alpha amino acids, to be specific, will look a bit like this. You will have a carboxylic acid groups. We've seen carboxylic acid, and then you will have an R group attached to that carbon, and you will have an amine at one end. So the name amino acid refers to the fact that you've got an amine there, and you've also got a carboxylic acid group there. Okay, and the amine of your amino acid will behave in much the same way as the amine, so the amines that you've seen. So a primary amine, for instance. Okay, so if we look at the behavior as nucleophiles, so there are a number of reactions you could carry out. For instance, if you wanted to form, if we start by looking at the formation of amines, you can look at, for instance, the reaction of ammonia. So using ammonia to as a nucleophile to attack a halogenoalkane. So if we look at this reaction here, where ammonia is reacting with bromoethane, you can show a curly arrow mechanism. So this is going back to your work in the first year. You can show a curly arrow mechanism from that lone pair to the carbon of your CBr bond. Why can you do that? You've got a delta plus on that carbon and a delta minus on the bromine. So there is a permanent dipole there, bromine being more electronegative than that carbon atom. And as a result of the incoming sort of pair of electrons forming a bond to that carbon, the electrons in the CBr bond are repelled. Okay, so they are going to be pushed away, and you're going to end up with a bromide leaving group. Okay, so you've got, as a result, and okay, so that's your ammonium species. Now, if we draw, perhaps we draw that to show one of the hydrogen bonds, so that we can do the rest of the mechanism. So if we have that hydrogen here, that hydrogen will be lost to, and again, ammonia being present will act as the base here, but we don't need to show that. So that bond is broken, and that leads to the formation of that amine, so ethyl amine is formed. So that's an example of a nucleophilic substitution mechanism, something that you would have encountered in the first year. Okay, so nucleophilic substitution, where the nucleophile is the ammonia molecule. Of course, the amine that you've just formed can be a nucleophile itself. So if you used an excess of halogenoalkane, then the amine you formed can go on to, we do this in blue, can go on to react further with any excess halogenoalkane. Okay, so we had some more of that, then you would go on to form this species here. And okay, so that would be an example of a secondary amine. And again, that would be via a nucleophilic substitution mechanism. Okay, so we've looked at amines. We haven't said much about amino acids or amides yet, but if you consider what you've just seen with the ammonia and with the amine of your ethyl amine, then you can apply the same idea to the NH2 group of your amino acid. If we quickly look at how amides are formed, these will be via the reaction of an amine, such as if we sort of tidy up the page a little bit. So we put a divider there. Let's go back one. There. Let's try that again. That's a nice straight line. There we go. And if we do that, okay, fantastic. So if we consider how an amide is formed, so you would need an amine such as ethylamine, and you would need to react it with an acyl chloride, so a bit like a molecule such as ethanoyl chloride. And just as you've seen alcohols forming esters when reacting with your acyl chloride, you will end up forming amide, and the amide bond looks as shown here. I'll highlight the amide bond for you. So the amide bond consists of a carbonyl group, and that carbonyl group is directly bonded to a nitrogen atom. Okay, so that's an example of an amide group. Okay, so we don't need to, for this particular reaction, we don't need to worry about the mechanism. We just need to know the product formed is an amide, and that you do end up with a small molecule. It's a condensation reaction, so you do end up with a small molecule, in this case, hydrochloric acid. So you can imagine or apply the formation of the amide shown here to the amino acid reacting with a carboxylic acid group. So the amine of the amino acid reacting with the carboxyl group of another amino acid. And in that way, you end up with a polymerization reaction in which you end up with a polypeptide. Now, in amino acids, the amide bond formed is known as a peptide bond. Okay, there's no difference between that amide and the amide from a normal amine and a carboxylic acid group. Okay. Okay, so we've already seen nucleophilic substitution mechanism, so we're not going to sort of show that again. Okay, so amines will behave as nucleophiles and will sort of attack electrophiles. So anything with a positive charge or a delta plus charge, amines can attack, and they can form amides. We've just seen that. And amino acids will behave, or the amines of amino acids will behave in the same way as normal amines. Okay, so there are no mechanisms to look at here. We can look at polymerization involving amino acids and perhaps diamines and diacyl chlorides very shortly. Okay, so polymers. If we consider the amino acid we saw on the previous page, I change over to a pen. So we had an NH2 group and then carboxylic acid group. That you can have this amino acid, say, reacting with a second amino acid, and you can call that R, and in forming this dipeptide, you will end up with an NH2 group at that end and an R group here, and then the peptide bond, so the amide in a dipeptide is referred to as a peptide bond, and there's our R dash group there. Okay, so what we formed here is a dipeptide, and so we've got an amide linkage being formed using these two groups here. Okay, so there we go. And as a result of the formation of that amide or peptide bond, you do end up with water being released. Okay, and of course the reaction could have happened with the carboxylic acid group of this species reacting with that amine of that species there. Okay, so you've got a dipeptide or two possible dipeptides being formed here. Now, we can hydrolyze amide bonds just as we can hydrolyze esters. So we could break that amide linkage here. We haven't looked at hydrolysis of esters yet, but we'll take this opportunity to show the hydrolysis of that amide. So if we carried out acid hydrolysis, so we used dilute hydrochloric acid or dilute sulfuric acid, then you would end up forming the ammonium species shown there, and you would have your carboxylic acid group. Because we've got acidic conditions, the amine is protonated, and over on the right hand side you would end up with, again, your ammonium species and your R1 and your carboxylic acid group. Okay, and if you carried out an alkaline hydrolysis, so in this instance you would end up with the NH2 group unprotonated, and you would have your R group, and because you've got alkaline conditions, the carboxylic acid group is deprotonated, so you've got a carboxylate group, and you would over on the other side have an NH2 group and your R prime or R1 or R dash, and the same carboxylate group. Okay, so when hydrolyzing amides or esters, do pay attention to the conditions. If you're hydrolyzing under acidic conditions, then the products will be, or any basic groups will be protonated, so amines will be protonated. And if you're hydrolyzing under alkaline conditions, then the acidic groups, the carboxylic acid groups, will be deprotonated, so you would have a carboxylate group. Okay, so that's so not quite a look at polymers just yet. I've shown you a dipeptide. But if we consider that you can have several of these amino acids as shown here, so if we had N, where N is of the order of thousands of those amino acids, and a similar number for that, then you would end up with an amino acid that has got this particular dipeptide here as its repeating unit. Okay, so you would, if I highlight this, or perhaps redraw that, let's redraw that here. So if we had that happening, you would form an amino acid that would have as its repeating unit R group there, and then you've got your amide, and then you've got your R prime and your carbonyl group. Okay, so that would be the repeating unit, if I can highlight that and annotate that. So that would be the repeating unit for the polypeptide. Okay, so that would be an example of condensation polymerization. And of course, with amino acids, you've got each monomer having both an amine and a carboxylic acid group. Of course, you can have condensation polymers formed where your both amines are on the same monomer and both carboxylic acid or groups are on a second monomer. Okay, so for instance, you could have by perhaps make room here. So for instance, you could have a diamine, and so we have this entity here, the ethane 1,2-diamine reacting with this diacyl chloride here. Okay, so instead of having an amino acid, you could have a diamine and a dicarboxylic acid, and you could have a very large number of that and a very large number of that. And of course, the repeat unit, the repeating unit, would be as shown, where you form amide, and we've got 1, 2 carbon between the diacyl fluoride groups. Okay, so that would be the repeat unit for this particular polymer. Okay, now we've got a few minutes to spare, so we can, if I just very quickly check that there aren't any questions for me on YouTube. Note there aren't, and then we can then go back to looking at some practice questions from an exam paper, and I've chosen the 2017 A-level paper 2, and if I just very quickly pick that out for you, there we go, June 2017, and there are some good questions on some of the organic topics we've just covered in this session. The first one shows the nitration of our benzoic acid. Okay, so we've got HNO3, we've also got H2SO4. We're also outlining the mechanism for this nitration of benzoic acid and show how H2SO4 behaves as a catalyst. Okay, so the first thing we need to consider is the reaction of H2SO4 with nitric acid. Okay, so this will lead to the formation of H2NO3 plus, and it would also form HSO4 minus. Okay, and then your H2NO3 plus will decompose to give you H2O and NO2 plus. Okay, so the mechanism is as follows. So we've got benzoic acid. Now the carboxylic acid is an electron withdrawing group, so it will direct to the 3 position. Okay, so if you note the NO2 isn't 1 away from your carboxylic acid group, it's 2 away, so it's at the 3 position. So that's what electron withdrawing groups already attached to the benzene ring do to any incoming substituents. So here is our NO2 plus. I draw it here. And then if we draw a curly arrow from our pi electrons to the NO2 plus, and okay, so if we show the pi electron density as such, okay, and making sure that it doesn't go beyond carbon number 2 and so carbon number 5 as far as the position of your electrophile is concerned. So we've got our NO2 there, and we've got our hydrogen there. Okay, and then we're going to restore the aromaticity of our ring by breaking the CH bond. So show that by drawing a curly arrow from the middle of the CH bond back into your benzene to form a full complement of 6 pi electrons. So we've got our NO2 formed. Okay, so we've been asked to outline the mechanism for this nitration of benzoic acid, but we're also asked to show how H2SO4 behaves as a catalyst. So having formed our nitrobenzoic acid and produced an H+, that H+, if we show this in red, the H+ formed, I highlight it, that H+ there, it will react with your HSO4 minus to reform your H2SO4. So there's your catalyst H2SO4, not used up in this reaction. It is initially reacted with nitric acid, but it is reformed at the end so that it is catalytic. It hasn't been used up. Okay, so In part 2, it says a chemist carries out the reaction in equation 17.1. This is a calculation, so I'm going to skip it, not because it isn't important, but we're focusing on so the organic reactions and mechanisms shown. Okay, so the next question, so part B, says the student investigates the relative ease of nitration of phenol, benzene, and benzoic acid. We've got some data looking at the conditions of nitration. We've got dilute nitric acid at 20 degrees Celsius and no catalyst needed for phenol. Benzene, you've got concentrated nitric acid, 55 degrees, so a bit warmer, and you need a sulfuric acid catalyst. And benzoic acid, which requires concentrated nitric acid and even higher temperatures of 100 degrees Celsius and your sulfuric acid catalyst. State the trend in the relative ease of nitration of phenol, benzene, and benzoic acid. So the trend is that nitration gets harder. So phenol is easiest to nitrate. And benzoic acid is the hardest to nitrate. Okay, so that is simply stating your a rather straightforward conclusion from the data we've been given. Okay, so looking at the temperatures especially and whether a catalyst is required or not. Okay, says apply your knowledge of the bonding in arenes to explain the trend in part B, part 1. Okay, so phenol is easiest to nitrate because lone pair of phenol OH delocalizes into pi system. Phenol is therefore has a higher electron density, has highest electron density, and it is the most nucleophilic. Okay, and if we consider benzene, benzene is electron poor. There's no delocalization into the pi ring. If we consider benzoic acid is an electron withdrawing group, so TOH is an electron withdrawing group and makes the benzene ring have less electron density. So poorer nucleophile. Okay, so we need to consider the two groups attached to the benzene ring. So the OH group, which is an electron donor, and will enrich the pi system when the lone pair delocalizes into the pi system, whereas the carboxylic acid group pulls electron density out of the pi system so that it's got less electron density, making it a poorer nucleophile. Of course, benzene will be in the middle because it has no substituent. Okay, so applying some of what we've just been looking at. Okay, and we can finish on part C. So if we look at the bromination of nitro benzene, so you're going to need, so the nitro group is an electron withdrawing group, so you're probably going to need a halogen carrier catalyst. So we could use AlBr3, and we would need bromine. Okay, so those would be the reagents, and the species form will be as shown. Again, if it's an electron withdrawing group, it will direct to the 3 positions. We've got NO2 here, so 3 position is there, and that's where your Br is going to go. And if you're going to reduce your nitro group to the amine, you're going to need tin and HCl. Okay, so that should take us to our bromophenylamine. Another student attempts the same synthesis but carries out reduction before bromination. The student is surprised to find that 2 structural isomers of 3-bromophenylamine has been formed into the desired product. So explain this result and suggest the structures of the 2 isomers. So if you carry out reduction first, you're going to form phenylamine. And if you form phenylamine, because it's an electron donating group, it's going to be directing to the 2 position. Okay, and so not just the 2 position, but also the 4 position. And so the 2 structures you're going to be forming. So if you form your amine first, you're going to end up with bromination at that position, and also bromination at the 4 position. So you could also have the species here. Okay, so apologies for writing BR2. Let's get rid of that 2 there. Okay, so you've got bromination at those 2 positions. You could also have the dibromo compound as well. Okay, so your amine, phenylamine, or amine group, NH2 group is electron donor. The lone pair delocalizes into benzene ring. Making it, so NH2 group is an electron donor. The lone pair will make your benzene ring sort of more have a higher electron density, and this directs to the 2 and 4 positions. Okay, so okay, and directs to 2 and 4 positions. Okay, so it has been quite a whirlwind sort of tour of a huge amount of organic chemistry that you've seen in the second year. And it's always important to point out that you need to sort of essentially tackle lots of questions and do so without your notes to really find out if you can record accurately the reactions and reagents, and also if you recall accurately and draw accurately the mechanisms you need to know. Just because it's a review of A2 organic chemistry doesn't mean that you should forget to sort of learn about your AS chemistry and to apply what you know from AS organic chemistry when necessary. We saw in one of the questions we looked at where you had to know a bit about nucleophilic substitution from the first year. So in revising organic chemistry, treat your revision process as a holistic sort of take on first and second year organic chemistry. Tackle lots of questions, and certainly when you've done these questions, do mark them using a mark scheme. And if you're unsure, if you're unsure what the mark scheme is saying, then do get in touch with your teacher and make sure that any gaps are sort of filled in. Okay, so I'm going to call it a day. It's been a pleasure as usual to host this live session. If you do have any questions, if you have enjoyed this session, then do like us, and certainly do give us feedback. Go to bootsrevision.com to watch replays. Thank you very much for joining me. Hope to see you soon.